Welcome back, everyone, for part 2 of our approaches to stochastic simulation series. And in this session, we'll be talking about event-driven simulation as opposed to the discrete time simulation methods that we discussed in part 1. So another way to simulate stochastic epidemics, event-driven simulation. And I have a diagram to show how this will work. So say we have this small population with orange dots for susceptible individuals. Infectious will be blue individuals, recovered will be yellow individuals. So we start at time t0, and then instead of after a fixed amount of time, we have after tau1 amount of time drawn from a distribution, the first event happens, and that in this case is an individual gets infected. So then for the next event, we draw the time until the next event again, and in this case, the event is another infection, and we repeat this, drawing time until the event each time, and having the what type of event it is also determined. So this third event in this particular case was an individual recovering. So about these times or time between events, these are for the Gillespie simulation, and the types of models or model simulation methods that we'll be using are have exponential waiting times. So the taus, tau1, tau2, tau3, will be drawn from what's called a waiting time distribution. And in this case, for the model simulations that we'll be looking at, this distribution is exponential. So it can have different rates, but this distribution determines the tau values are drawn from the distribution. So the probability of, say, the days since infection being between 2 and 4 is the integral of the probability density function from 2 to 4. And the integral from 0 to infinity is 1, because the probability, it's a probability density function. So if you look over all of the possible values, you'll have the probability equaling 1. So to summarize, for the Gillespie algorithm assumptions, we have finite countable populations, which is nice. We tend to think of populations being finite. This is particularly important when they're small. We still have well-mixed contacts like we did in the deterministic differential equation models. And the waiting times, the time between events, are exponential. And this is important because it allows the system to have what's called the memorylessness property. And that property means that the update that you make to your system is only based on the current state and not any of the states previously. So for example, if I got infected 5 days ago and I have a friend that got infected 2 days ago, the chance that we recover by tomorrow is the same for both of us. The system doesn't remember when we got infected. And that's an important assumption to keep in mind when using the Gillespie algorithm for modeling your population or your system. So a few more notes. So noise or stochasticity is introduced by the discrete nature of individuals. And this is an event-driven simulation. So we're doing one event at a time. And because we're doing one event at a time, this can be computationally slow, especially for large populations. So let's go through the general idea of the associated lab that goes through this particular stochastic simulation method. So there are two things that we need to know in order to update the system. We need to know what happened. So in this case, there are two possibilities. A transmission event could have occurred or a recovery event could have occurred. And then we also need to know when did it happen? And that is determined by the rates. So we can see these rates are the same as our rates in the deterministic ordinary differential equation analog. And these rates, as we saw before, along with that exponential distribution, we're going to draw waiting times for the time between events. So they're going to be in the tutorial values called the event type and the event time. And at each step, we're going to have to figure out what the event type is and what the event time is. And the way we will do this is, so the time to the next event is going to be exponentially distributed with a rate that's the sum of the rates of the possible events. So in this case, it's just lambda1 plus lambda2. And then the probability that the event is of type I, p sub I, is lambda I over the sum of all of the rates. So again, only two choices here. But that will give us the probability that the event, that will help us determine what the event is. And it kind of makes, I don't know if intuitive is the right word, but so if you imagine one of the rates, say lambda 1 is much bigger than lambda 2, then the probability that the event is going to be a type 1 event is going to be bigger than the probability that the event is type 2. So again, another set of pseudocode for you. Again, define initial conditions always first. And then we have another loop. Always want to have while the infectious population is positive and the time is less than some specified maximum time that you've chosen, we're going to calculate the rates using these expressions, determine the time until the next event, and determine the event type. And then after we've done that, we update the state variables. So in this case, update S, I, and R, and we update the time. And this time update depends on that time that we drew, the time to the next event. So it'll be T, the current time, plus tau is what we'll add on to update the time of the system. So to summarize our overall, the stochastic simulation series, there are many sources of stochasticity, including small population size, imperfect observation of cases, and environmental variability. Can't stress the importance enough of small population sizes. That is maybe one of the first things I think about when I'm considering a deterministic or a stochastic model. Is what's the population size I'm thinking about. And this also could be, it might not be the total population size, say, of a city. If the number of infectious individuals in the city is small, stochasticity might play a substantial role, and you might want a stochastic model. So we have the Reed-Frost model as a discrete time model where the time step is based on the infectious period. And this idea can be extended into the stochastic Reed-Frost model. And if we string those binomial draws together, we get chain binomial models. And so these have an arbitrary time step and infectious period duration. And so those are the discrete time stochastic simulation methods from part 1. And then part 2, we saw event-driven simulations, which to me at least are a bit more intuitive because each event is modeled separately, but these methods can be computationally slow, especially for large populations. So that is the end of this series.